Alright, so this is the dragging dresser problem. So what we got here going on is we got the it's the coefficient of kinetic frictions right here, and then this is set up to 90 degrees, and it's from 0 to 90 degrees. This is the amount of times the for loop goes through. So basically what I did here is that I modeled the equation right here. The f prime equals mu over cosine theta plus mu sine theta. So you have the cosine here, you have the sine here, and then the iteration, basically it wasn't converting from the integer to a double, but had to convert it by an integer to a double. This goes into the degrees to radians, it goes into sine, and then the numeric control goes into this, goes into multiplication, the plus function, and the division function. And because this is the equation right here, this is this. And then this is connected to an array, and this is an indicator attached to the waveform graph. And then determine the angle at which f prime is smallest, and minimum magnitude force is required to drag a dresser at constant velocity. So we're gonna run this. So the coefficient of friction, so slowly increasing. So the angle that hold on a second. The angle that would have the lowest amount of force required would be around right around 1.5, and then have an array at 7. Hold on. So because when we first graph it, when we increase the friction, when it's 0, it takes a lot more force. Basically, when it's 0, the force takes a lot more to it takes a lot more to push it. The more the coefficient of kinetic friction is at 0 degrees, but as it approaches 0, as it approaches 90, it gets, as the angle approaches 90, it takes a less amount of force to push it. So you would have to push it at around, it takes the minimum constant velocity. So it would be around 1. It would take around 1 Newton of force to, that's 1 Newton of force is the minimum magnitude force is required to drag a dresser to constant velocity. That took a lot longer than expected to explain, but that is the program that's running.